Totally, how many participants are there, sir?
33, sir.
33.
No, total around 150.
150. Okay.
Yeah. So basically, the session will start at 9:30. The people will join accordingly.
Okay. Good morning, Mathur, sir. Good morning. Myself, Krishna Kumar. VSSC earlier, retired. How are you, sir?
Yeah, fine. Good morning.
Good morning, sir. How are you?
Yes, was doing great.
How is Delhi? Whether cold started, winter started?
Yeah, just
Okay.
much better than last week.
Oh, I see.
But again, this thing, smog and all that, that is also started.
Because of the pollution.
Yeah.
Because December only, usually
Yeah.
there's smoke.
Today morning
Fog plus
itself.
smoke.
Yeah. It's not fog, but smoke.
Smoke. Smoke plus fog will come smog.
Yeah, that will be in December.
Oh, that will be in December. Okay.
Yeah.
Our Seth ji has come. Okay, Seth.
No, doctor. I think he is not in touch.
Okay.
Acha, RK Seth.
RK Seth.
Yeah. He
Will be
will
coming.
join. Yeah,
Oh,
he
he
will
will
join.
join.
Yeah.
Okay.
So we are at NPL right now.
Okay.
So
Seth ji is also at NPL, you know.
Who?
Seth, RK Seth also at NPL.
Yeah, he's right now. Maybe he's in his office.
Okay.
So we are in the conference room here at NPL.
Okay.
Yeah. So most of them will join from their residence itself.
Yeah. That's also possible.
Yeah.
Hello, good morning. Am I audible, sir?
Yeah.
Hello.
Hello. Hello. Good morning, Manoj.
Good morning, sir.
Morning. How are you? So Manoj, you are in which department?
Sir, I am in Advanced Carbon Products of CSIR National Physical Laboratory.
Okay. That is New Delhi.
Yes, sir.
Okay. You are along with our RK Seth ji?
Sir, I am under the supervision of Dr. Bhanu Pratap Singh.
Okay. VP Singh ji. Okay.
Yes, sir.
Okay.
Oh, okay. Good morning, all. To start with the proceedings of the day, two Manchester researchers who isolated the world's first so-called two-dimensional material went on to be rewarded with one of the highest accolades in science. The Nobel Prize for Physics in 2010 went to Andrei Gain and Kostya Novoselov for groundbreaking experiments regarding the two-dimensional material graphene. However, their path to laureate status was almost by accident. Indeed, it was sheer playful curiosity in a Friday night experiment where they managed to reduce graphite to single atomic layer using a Scotch tape. However, as Novoselov very truly explained in his words, I guess you can say it was an accident. And accidents are important in science first of all, but also accidents never happen accidentally. You actually need to create an environment for those accidents to happen. Respected learned delegates, hello, good morning, pranam, namaste. I, Manoj from CSIR National Physical Laboratory, is immensely pleased to extend you a very warm welcome on behalf of Indian Carbon Society and CSIR National Physical Laboratory, who has clubbed all of us together for this e-workshop on advances in science and technology of Graphene 2022. To start with proceedings of the day, I would like to request Dr. O.P. Behel, President, Indian Carbon Society, to welcome the dignitaries and delegates with his warm words. Over to you, sir.
Thank you very much, Manoj. Good morning.
Yeah. Can you hear me now? Yeah.
What do you do?
Professor Vinu Gopal,
Sir.
Ajanta, Dr. Dakate, Dr. Mathur, Bhanu, as we address him very affectionately all the time. invited speakers, participants, invited guests, ladies and gentlemen. A very good morning to all of you. A very special welcome to Professor Venugopal Achanta, Director, National Physical Laboratory. Professor Achanta has been supportive of this event in every respect and all the way when we thought of this idea of organizing this event. Thank you so much, sir, for being with us this morning in spite of your very busy schedule. A very hearty welcome to all the invited speakers for having agreed to share their research results for the benefit of the carbon community at large. It has not been very convenient for the speakers from across Europe, USA, and Australia to participate in view of the time difference that we have between us and those countries. In spite of all this, they have all who were invited agreed to share their knowledge, experiences, which is highly appreciated, and a very warm welcome, though virtual. I extend a very warm welcome to all the speakers, invited guests, and participants to this two-day workshop. Now, we are here, gentlemen, ladies and gentlemen, we are here to discuss progress in science and technology of this wonder material, graphene. If we really look at the last 50 to 60 years of scientific achievements, particularly in the area of materials, all through carbon has been providing paradigm-shifting technologies, namely, for example, few of them I will name: mesophase, carbon fibers, carbon nanotubes, and now graphene. These technologies have transformed sectors like defense, aerospace, nuclear energy, environment, to name a few. The last two discoveries, as already mentioned by my colleague earlier, have been awarded with Nobel Prizes. Now, I don't think we will be able to find another example in the area of material where the same material has been awarded twice in the last 35 years, a Nobel Prize. Now, graphene is, as I said earlier, is a wonder material. It is 200 times stronger than steel and 5 times lighter than aluminum, along with unique electrical and thermal properties. These properties are being exploited very fast all over the world, and that's why this workshop. Applications of graphene are numerous. It is very difficult to touch all of them, but I'm tempted to bring to your kind attention at least 2 or 3 of them. The most important being, which will affect everybody as a common man as well, graphene-based super fast charging batteries. Now, these batteries have charging time. They can charge the cell phone in less than 30 minutes, as against a couple of hours in the case of cell phones, which are normally being available today in the market. Another thing is graphene touch screens are flexible, strong, and unbreakable. I'm very glad to share with you that Samsung, which is a leading company in cell manufacturing, has already announced such cell phones coming up in the market very soon, which will have the benefit of both these technologies. Maybe very soon, batteries will become obsolete in view of the very fast coming graphene super capacitors. So there is a challenge, opportunity, and excitement. I urge all the participants to take full advantage of this opportunity, which is being provided by the Indian Carbon Society, the opportunity of listening to the experts. I urge you once again, accept the challenge and exploit the opportunity. And once again, I welcome you all and wish you all the best for the conference. Thank you so much.
Thank you, sir. Good morning.
Thank you, sir, for your warm welcome address and information. Now, I would request Dr. R.B. Mathur, Secretary of Indian Carbon Society, to brief us about this workshop. Over to you, sir.
Is it okay? Am I
Yes, sir.
audible?
Yeah, audible, sir.
Good morning to everyone
Morning.
and welcome to the workshop on Graphene 2022. Now, from the ages, carbon is surprising scientists and technologists with the discovery of its newer and near forms, as explained by Dr. Behel. And besides the conventional form of two allotropes in diamond and graphite, so we have come across many other products from carbon, like carbon fibers, fullerenes, carbon nanotubes, right from 1960s to 1990s, until a newer form of graphene was produced in a laboratory in 2004 by Russian-born scientists Andrei Gaim and Konstantin Novlaskov. Because of its unique structure and properties, we can see graphene as an exciting replacement for existing materials that have been pushed to their physical limits. Graphene could therefore revolutionize other areas of technology constrained by conventional materials. For example, energy storage devices, advanced nanocomposites, electronics, quantum-based devices, sensors, and many more other applications, which will, these technologies will boost the aerospace, defense, nuclear, and other industrial sectors. However, it is important to note here that we should not get carried away with the hype. Most of the exciting work in the graphene still has so far been done on a very small scale and in chemical and physics laboratories, and very few technologies have seen their commercialization. Most of the research is still what we would describe as blue sky. It could be many years or even decades before it can mature practically, let alone cost effectively. Therefore, it becomes all the more important to take a stock of the R&D efforts taking place globally and assess the progress made so far in this field. Indian Carbon Society has from time to time endeavored in promoting the growth of research and development of carbon science and technology in the country, those through synergy of industry and institutes engaged in the field of carbon by regularly holding conferences, seminars, and workshops at different centers in the country. In continuation to our objectives, it is proposed to hold this workshop on graphene to take stock of the expertise and present scenario of R&D in various institutes and carbon industries, which will define a roadmap to enable the country to demonstrate its commercial applications. I am grateful to all the invited speakers from India and abroad who have kindly agreed to share their expertise in this field, along with the researchers who are going to present their work on graphene. And I am sure it will benefit the researchers and industries in the country in their future endeavor on graphene. With this, I would like to once again thank you all for your participation. Thank you.
Thank you, sir.
Thank you very much, sir, for your for your warm words and valuable information. CSIR National Physical Laboratory has also been actively contributing to the knowledge and science of graphene over the years. Dr. S.R. Dakate, Chief Scientist and also leader of the Carbon Group at National Physical Laboratory, will now brief us regarding the research activities related to graphene carried out at CSIR NPL. We welcome you, sir.
Okay, good morning to everyone. Dr. Bayal, Dr. Mathur, our director, Professor Rajanta Venugopal, our invited speaker, Professor Ravinder Ghosh from ISC Bangalore, Professor Mandar Deshmukh from TFIR, Mumbai, and other delegates. So,
Video
about
not seen. It's not visible. Video not seen.
It does not matter. So, anyway.
Sound is audible, but your photo is not seen.
Okay, so the graphene work in NPL.
Yeah, now visible. Thank you.
Initiated since NPL is working on the graphene related activities from 2009 onwards, and this carbon group of National Physical Laboratory is involving on working on various form of carbon, and this group has been established before 1960 and working on various form and developed a number of technologies, and technology has been transferred to the industry. So from 2009, NPL started working on the graphene synthesis. First time we have published one paper, 2-3 paper in Carbon Journal on the single layer graphene synthesized by the exploited graphite as well as unzipping of carbon nanotube. Later on, we have initiated work on the synthesis of graphene by chemical vapor deposition technique and development of device from the single layer graphene, bilayer graphene, twisted graphene, and also NPL is working on the single layer graphene from epitaxial growth process. Apart from particularly NPL group is working on the structural material. So in structural material, the single layer graphene synthesized by CVD method is not sufficient and we require bulk amount of graphene. So we are working on the graphene derived different graphene derivatives such as graphene oxide, reduced graphene oxide, functionalized graphene oxide. Okay, and that will be used, that we are using for development of nanocomposites for different applications. But overall, if you see in the world, a lot of work is going on the graphene, but still there is a requirement of standardization of this material. So how we can do the standard, even though we are doing some experiment, we are getting some good result, we are developing very good graphene, but its repeatability and reproducibility is one of the important problem, and we are characterizing this material, their properties also reproduce and repeatable. So for this international intercomparison and your quality infrastructure is very much important. In this direction, National Physical Laboratory is working on the standardization of this graphene material by different techniques. So there is a VAMAS, Versatile Project on Advanced Material. India is representing on that organization. And there are a lot of projects on the graphene standardization. So NPL is taking part in this program for international intercomparison for standardization of graphene by different techniques. Such as there are 12 projects in this program, and NPL is contributing in 3 different programs. And each program, if you want to characterize the graphene or standardize the graphene, there are 12 laboratories involving in the characterization of same material with the standard protocol. Okay, so whatever instrument we have at different laboratories, our material should perform same result. They can give the same result. So the result should be reproducible. So in this direction, NPL working on the VAMAS TWA 41 project. If you see anybody interested, they can go and visit vamas.org. So there are different projects, 12 projects are going on the graphene characterization. Means that is particularly we have to characterize, produce the reproducible and repeatable data. Then that data will be standardized and sent to the standard committee for making the ISO standard. So in this case, at present, NPL is working on distribution of lateral size and thickness of few layer graphene flakes using scanning electron microscope and atomic force microscope. And this project leader is NPL UK. There are 15 laboratories, particularly National Measurement Institute of the world involved for characterization of this graphene by scanning electron microscope and atomic force microscope. Another project NPL is working on validation of graphene by Raman spectroscopy for determination of number of layer of graphene nanoplates. So this all this material now developed by the industry, not individual laboratory, because individual laboratory have the limitation. We can develop few gram, yeah. So that is not sufficient for standardization. We require in bulk amount of graphene. So bulk amount of graphene only can be developed by the industry, and that will be, we have to standardize. We have to develop the standard procedure for ensure the quality of the graphene. So another one project NPL is working on structural characteristics CVD growth graphene by coverage of substrate, number of layer, and level of disorder, again by Raman spectroscopy. So such type of initiative is required by the graphene research community to whatever we are working, but that should be standardized. Whatever we are claiming our data, that should be acceptable by the international community, and that will only happen. We can intercomparison our result, we can characterize our data, our samples with other laboratories, and we can find out what is the uncertainty level in our measurement. So that is very much important. So by these few words, I am now closing my remark, and thank you very much, and good luck for this 2-day workshop. E-workshop is fruitful for the graphene working community. Thank you very much.
Thank you.
Thank you for your wishes and information, sir. Let us now have the pleasure of hearing from Director CSIR NPL, Professor Venugopal Achanta, through his inaugural address. We welcome you, sir.
Thank you. First to the Indian Carbon Society, which we treat as part and parcel of NPL. Thanks to Dr. Bal and Dr. Mathur for their continued contribution to the Carbon Society and promotion of carbon-related materials through the society activities. Right. So, I'd like to thank on behalf of NPL and the organizers, all the invited speakers and the participants for accepting our invitation and participating in this conference. Right. So we heard about the graphene contributions and the importance of graphene, but in my role, so I just want to inform a little bit about NPL. National Physical Laboratory, as most of you know, is the National Metrology Institute. So we have 3 major activities which go on at NPL. One is the metrology as the National Metrology Institute, and the second one is material science, and the third is the environmental sciences. So these are the 3 major activities which we can classify our work in. So most of these things which we would like eventually as an NMI is to contribute towards the metrology activities, because the quality infrastructure in the country depends on the primary standards which we set up at NMI. Right. So what I would love to see at the end of this meeting is more interaction between the metrologists and the material scientists, so that we can promote eventually application of these materials to metrology. And in the process, I would love to see more interaction between the Metrology Institute, NMI, and the universities. So this is something which is lacking right now. We need to promote more interactions. We cannot do everything in-house. So we need to collaborate, we need to cooperate with experts from across India, so that we can develop and establish better facilities for the nation. Right? So for this, we need to look at opportunities so that we can work together. So this hopefully in the next year or 2 will come up with some funding and some procedure in place so that we can interact more with the universities. So we need to have more such conferences so that we can rope in the experts in the country, bring them to see what we can do together with the NPL. I really hope to see at the end of the meeting a 1 or 2 page report, so areas where we can work together. Okay. So thank you once again, and I look forward to listening to the excellent talks which are scheduled in the program. Thank you.
Thank you, sir, for your nice words. We also do hope that it will be such a healthy discussion in this workshop. May I now request Dr. Bhanu Pratap Singh, convener of this workshop, to propose vote of thanks to the delegates.
Very good morning to all. On behalf of organizing committee, I'm glad to be here to express my vote of thanks. First of all, I'm very thankful to our director, Professor Venugopal Achanta, for always supporting us for organizing this workshop. A special thanks to all the invited speakers for accepting our invitation. Professor Arindam Ghosh from ISC Bangalore, Professor Mandar M. Deshmukh, TIFR Mumbai, Professor Marc Montieu, CMES France, Mr. P.S. Jain, Carborundum Universal Limited, Ernakulam, Professor Appa M. Rao, Clemson University, USA, Professor Ajanu, the University of Newcastle, Australia. Dr. H.S. Bist from Reliance Industry Limited. Thank you, sir. I'm also thankful to all the organizing committee members for their support in each and every step. Starting from Dr. O.P. Behel, the chairman of this workshop, Professor L.M. Manocha, co-chairman of the workshop, Dr. R.B. Technical Committee Chairman, Dr. S.R. Dhakate, Technical Committee Co-Chairman, Dr. P.K. Jain, R.G. Shah, and Mr. R.K. Seth, the coordinator of this workshop. I'm also very thankful to my colleague, Dr. K.M. Subedar, the co-convener of the workshop. He's always with me in organizing this workshop. I'm also thankful to all the delegates of the workshop, oral paper presenter and poster presenter who have joined here from various parts of the country. I'm also very thankful to all the chairmen and judges of the various sessions who accepted our invitation, starting from some of the from the National Physical Laboratory, some other place, from IIT Delhi, Professor Veena Chaudhary, Dr. P.K. Jain from ARCI Hyderabad, our own colleagues also. I'm very much thankful to Reliance Industry Limited, who is for sponsorship of this workshop. Thank you all.
Thank you. Thank you.
Thank you, Bhanu sir. Now it's time to start our first session of the day, chaired by Dr. O.P. Behel. It is a great honor for me to introduce you all with the Carbon Man of India, Dr. O.P. Behel, although he does not like to be called that. But sir, we do love to call you that. He's a retired chief scientist of CSIR National Physical Laboratory, Delhi, where he led the Carbon Group for 19 years. During his leadership, Carbon Research Group accomplished several major projects, including development of carbon-carbon composites for Agni Missile Development Program. He has been decorated with several national and international awards, including NRDC Technology Award and MRSI Medal Award 1991. He is also a fellow of National Academy of Sciences. His eminent publications are still a guiding torch to young research scholars like us. We can go on and on with his countless achievements and traits. However, the watch as well as Behel sir do not permit us for so. Therefore, with no further delay, I would invite Dr. O.P. Behel sir to the digital podium to chair the first session of the day. Over to you, sir.
Audible. Not audible.
So thank you so much, Manoj. You have been very liberal in introducing me. Thank you very much indeed, and thank you all for all of you being here. Now, I have the pleasure of inviting Professor Andam Ghosh. Professor Ghosh is a professor at the Department of Physics, Indian Institute of Science, Bangalore. Professor Ghosh majored in physics from Calcutta University in the year 1991. And following the graduation, he moved to Indian Institute of Science, Bangalore, where he did his master's in 1994 and continued his studies and got his PhD from there itself in the year 1999 in physics. He was then a postdoctoral research associate at the University of Cambridge for 5 years. And also in between, he was a visiting research fellow in nanotechnology in USA. Professor Ghosh has published a large number of papers in high impact journals like Nature Physics, Nature Nanotechnology, Nature Communications, etc., etc. Professor Ghosh's interests have been, scientific interests have been experimental condensed matter physics, electrical transport and noise in atomic membranes and nano devices. And he has been, Professor Ghosh has been recipient of several awards and honors. I think the very glaring example is that he was awarded the Infosys Prize for Physical Sciences, which is the most prestigious award that recognizes the achievements in science and research in India. So that is great, Professor Ghosh. We congratulate you for that. He has been also recipient of Atomic Energy Raja Ramana Prize lecture in physics in 2017 and Shanti Swarup Bhatnagar Award, which he was given in 2012. There's a long list of other awards as well. I would not like to hold between the audience and him anymore. May I invite Professor Ghosh to please start his lecture. We to which we look forward very eagerly. Professor Ghosh.
Thank you, Dr. Bal. Can you hear me?
Yes, I can.
Well, let me first share my screen, if it's okay. Can you see the screen?
Yes, sir.
Wonderful. Okay, so I think we are all set. First of all, again, let me thank you, Dr. Bal, for a very kind introduction. I am delighted to be here. And it was particularly nice to listen to the first few introductory remarks from from your very esteemed delegates, because that also gave me a little bit of sense of what would be of interest to see the carbon, graphene, and in general 2D material expand in India and globally as well. There are certain problems that we have which are not just Indian problems. It is very global. So what I will do today is I will tell you a bit about what the research, R&D, and what kind of new phenomena, what kind of new directions of research that we can all go through. But if I get time for the last 5-7 minutes, I'm also going to add a little bit about where the graphene as a material can make an impact, how all these new research, the global research that is happening, can actually be taken to reality. So let me see if I get time. So let me get started. So the original plan will be as I mentioned, that is, I will tell you a little bit about the new direction of graphene that's that's taking up a lot of global interest today, which is essentially twisted bilayer graphene. And there are new physics in this. People are looking for various kinds of phenomena like superconductivity, etc., and also looking for new states or quantum states of matter. So basically, we have been working in this field for last few years, and it's been a PhD projects of at least 3 students. Let me just put my pointer. Yeah. Right. So what I'm going to do today is I'll restrict myself to one aspect. Well, this recent paper which has just come out on this topic, this has been done in collaboration with several of my colleagues who are theoretical physicists as well as experimental colleagues. And one of the collaborators who gave us very high quality boron nitride are in Japan, Kenji Watanabe and Takashi Taniguchi. All right. So basically, what's the interest in this twisted bilayer graphene? Graphene itself is a hexagonal crystal structure, and it has a Brillouin zone, which is also a hexagonal. It has got 2 different types of values called K and K prime. These are very fundamental physics of graphene, which everybody now knows. But single layer graphene has its own electronic bands. What happens is these bands have been explored enormously from many points of view. But now, by putting another layer of graphene, there is a way to change the electronic bands in a fundamental way. So basically, that's what twisted bilayer graphene is. You start with one graphene, you put another layer of graphene on top, and these are usually at this point of time done by mechanical exfoliation. You take a mechanically exfoliated graphene and you put another layer on top. And then you start rotating one graphene with respect to the other. And if you keep on rotating, you can see there's a new lattice structure that develops. And this lattice structure is much larger than single hexagonal crystal structure of graphene. So as a result, this is also, this gives a Brillouin zone, which is much smaller, and that folds the energy bands and renormalizes various properties of the energy band. And this is called a moidal lattice. Okay? So basic idea here, you have large graphene bands, which are rotated, 2 graphene bands, which are rotated with respect to each other, and you get a very small band, which is called a small Brillouin zone, which corresponds to this new lattice structure that has developed as a moidal lattice. Now, what happens is, if you look at the energy bands, a very easy way to understand the new bands is as if they have been repelled or flattened because of the two graphene layers are interacting with each other. That means, for example, this is the original old bands. And you can see when the two graphene layers, the blue and the red ones, they start interacting, the new bands are essentially formed, which are flatter than the old bands. And this flatness is very important because when you make the electronic energy bands flatter, the density of states increase, and that leads to new physics, strong correlation physics. And that's what we have been interested in. And many of the phenomena that are connected to this twisted bilayer graphene is connected to strong Coulomb interaction that comes from this flattening of the band. There is one more interesting aspect that one needs to talk about, that is the density of states. See, when you have these flat bands, you have the density of states which are zero at the edge of the bands, and this is called a Moire gap. But at the center of the band, because of these flat regions, there is a very large energy, large density of states, and these are called van of singularities. Okay, this one and this one. So most of our experiments that we do in the lab are confined to this low energy Moire band. We usually don't go to much higher energy, but mostly confine ourselves in this low energy Moire bands and change our electron density or Fermi energy between these bands using electrostatic means. We put these on a field effect transistor, and we start changing the Fermi energy, and if Fermi energy goes through all these density of state of the band energies. Now, one of the key aspects that I'm going to talk about today is what is called a filling factor. That means by external means, by electrostatic means, how many electrons you put in a band or what fraction of the band is filled is called a filling factor. The filling factor is new. If this band can contain at the most N0 electrons or Ns, which I'm going to use later, then the density that exists divided by the maximum density that you can put in this band is called a filling factor. And N0 is nothing but the 4 comes from spin and 2 spins and 2 valleys, and that gives you 4. And divided by the area of the Moire cell, you can see this area, and that gives you the maximum number of electrons or holes you can put in any of these bands. So the filling factor is essentially the density divided by the maximum that you can put in over there. So what happens is when you have flat bands, you have very large density of states, and electron-electron interaction becomes really strong when you have the bands roughly around half filling. You can see these van of singularities are nearly about half filling, and this is a region where new physics can emerge, and this is what we had probed recently. So if you take 2 by 2 layers of graphene, the calculation shows that if the angle between 2 graphene layers is very large, then they essentially are decoupled. Their physics don't hybridize. The interesting thing happens when the graphene angle between the two graphene layers is in the order of 1.4 Kelvin and 4 degrees, and that leads to this flattening of the bands, and that leads to strong correlation physics. So this has led to a lot of very interesting new directions. The superconductivity has been found. There are a lot of new broken symmetry phases. There are spin Hall effects. There's new phases like lift-shift transitions. There are churn insulators. There are many interesting directions that have over the last 2 or 3 years have come up. One of the key questions, actually, when the superconductivity was discovered in this twisted bilayer graphene, people asked what's the origin of the superconductivity. It is still under debate. There is no clear understanding of where the superconductivity comes from. But there were certain parallels that were drawn with high temperature superconductors. The reason behind it is the following. So you see, in these systems, the superconducting phase is often observed very next to what you call a correlated insulator phase. And this happens at the filling factor of 2. As I told you, when the filling factor of the band is around half filling, which is because there are 4 maximum states, then half filling is essentially a filling factor of 2. When you have a filling factor of -2 or +2, there's a correlated insulating phase, and the superconductor is observed right next to that. And this is exactly what happens in many of these high TC superconductors, where a Mott insulating phase is center, and the 2 superconducting domes are next to it. So it's a doped MOT insulators. So that led to very lot of interesting questions. And one of the questions was, okay, if it is a MOT insulator, then one of the key feature of those insulating superconducting phases in those high TC superconductors is the resistivity going as proportional to temperature, which is very different from a Fermi liquid expectation where the resistivity is supposed to go as T square. And this is why it's called a strange metal. Okay, so the controversial aspects that emerged is that do we have a system where the Fermi liquid theory is breaking down, or do you have a system where these are quantum critical systems? So this is one of the key questions that arose when the filling factor of this twisted bilayer graphene is close to ±2. So we wanted to ask this question with our technique, and one of the techniques that we wanted to use is called the thermoelectricity technique. And the reason thermoelectricity was used is because it is extremely sensitive probe to strong correlation effects or effects when the usual electron and hole quasi-particles do not exist and they become ill-defined. So we wanted to ask if around the filling factors of 2, the quasi-particles that we have in our system are indeed like a Fermi liquid or conventional metal or not. Okay, so that's what the reason why we wanted to use thermoelectricity will be getting clear now. So typically a quick primer, thermoelectricity is given by, if you apply a potential temperature difference, you get a voltage difference, and voltage difference divided by the temperature difference is called the Seebeck coefficient. And the Seebeck coefficient comes from 2 different sources, the thermal voltage. One is the diffusion thermopower, which essentially is a conventional Boltzmann distribution, and you have a MOT formula, which is a very robust formula, which comes because of the total current being dependent on the electric field that you apply and the temperature difference that you create, and that gives you a thermopower to be proportional to the derivative of the conductance with respect to energy. Now, this derivative can be split, and one of the advantages of using this kind of thermopower is that you can use part of you can verify this experimentally, because the conductance versus density is what you measure experimentally, and dN dE is nothing but the density of states. So from here, you can actually see whether your system is behaving like a conventional metal, which is diffusive, and if there's any deviation from this expression, then you know something interesting is happening. Okay. There is also another part which I'm not going to talk about today at all, which comes because of the electron-phonon coupling, and it's called the phonon drag of the thermopower component. I'm not going to talk about this at all. Instead, I'm going to use this expression where the thermopower or semi-classical thermopower is proportional to the derivative of conductance with respect to energy multiplied by the density of states, and see and compare this expectation with what we actually obtain experimentally when we do this experiment with twisted bilayer graphene. Okay, so this is just an example of how this formula works. So resistance as a function of gate voltage, usually in a graphene-based system, shows like this bell-shaped behavior. And you can see a typical device that we make in the laboratory. Here is a gated region, and by passing a heating current on one end of the sample, you create a temperature gradient across the sample in this direction. And the corresponding voltage that generates is given by VTH, and you can see this red curve is the thermal voltage, which looks almost like a derivative of the resistance versus gate voltage or density. And if I use the fact that this work was done with a bilayer graphene, and the bilayer graphene has density of states which is constant like a standard metal, then if I multiply the derivative of this conductance, which is here, and the constant density of states here, then you can see you can beautifully reproduce the experimental thermal voltage, which essentially tells us that bilayer graphene is a good quality semi-classical metal, and we don't have to worry too much about its very strong physics. I want to show you what happens when I use now, instead of a conventional graphene, but a twisted bilayer graphene. And that's where the fun starts happening. Now, quickly tell you how to make these kind of systems. They are not straightforward, because you are now taking two graphene layers and rotating them by a very accurate angle of 1 degree or so and making a new system. Okay? So this is called a tear and stack method. You can see the way it's done is that you take a layer of graphene and you take a layer of boron nitride and use the boron nitride to cut the graphene in half. And then you can see this, the boron nitride has taken the graphene out and it has cut it in half. And then you rotate with respect to the lower graphene, the amount you want to, and then put it back on the graphene. And then you get a twisted bilayer graphene. So if I look at to show you the actual image of a device, so you can see this originally, this one is the graphene, and this was a layer of boron nitride. You press the boron nitride on lower graphene, and then you lift it up so that the graphene gets exactly half, okay, or graphene gets cut along the edge of the boron nitride. And then what you do, you shift this and rotate it, and you essentially get the new system, which is the boron nitride. Underneath that, the twisted bilayer graphene after the angle that you have done. So our experiment essentially is this, that this is a total, then we pattern these twisted bilayers using electron beam lithography and put electrical contacts. And you can see that this layer is underneath this, you have the twisted bilayer region. And for thermoelectricity, we need a heater region. And for that, we need this part, which comes out a little bit. And this is a single layer region. So the lower one is the full one, and then an additional layer of another graphene, which is rotated by about 1 point some degrees, is kept on top. So this is how most of our graphene, twisted bilayer graphene devices are created. And then we pass a heating current in this direction to create a temperature difference along this and measure the resulting thermal voltage. Okay, so if I have the experiment that I'm going to show you was done at around theta, the two layers are rotated with respect to each other by about 1.6 degrees. The corresponding band structure calculation was done by my colleague Manish Jain and his student Shinjan Mandal. And their calculation and the density of states are shown here. You can see that density of states goes to 0 at 3 places. At this point, which is at the Moire gap, and this point, this is the other Moire gap on the other side, the whole side, and the charge neutrality point, which is here. Okay, so there are 3 different regions where the density of states goes to 0, which means that if I measure the electrical resistance of this system, I should get 3 peaks, and that's exactly what we get. You can clearly see that there are 3 different peaks. This peak corresponds to when the entire Fermi energy is at the Moire gap. So the band is completely filled from the electron side. This region is on the whole side entirely filled. And the center one is what we call the Dirac point. And you can see one of the interesting aspects is that when I look at the half filling, which is at the center point between these 2 peaks and these 2 peaks, this is the half filling points, these center lines. If I measure the electrical resistance as a function of temperature at this half filling, we see a linear temperature dependence over nearly 2.5 orders of magnitude of temperature. So all the way from 0.3, 0.4 Kelvin to about 200 odd Kelvin, we see really nice linear temperature dependence, which is one of the controversial points, that whether the system is obeying the Fermi liquid theory or not. Okay. So these two are essentially plotted to corresponding to this temperature, this gate voltage at half filling. Now, what happens if I do the thermoelectricity of these of this system? So you see, this is the 3 peaks. So if I do the thermoelectric voltage measurement, it should become a derivative of this resistance as a function of gate voltage multiplied by the density of states. Density of states was calculated by my colleague, and the electrical resistivity was measured in the experiment in the lab. So if I look at these 2 regions where density of the half filling, this one and this one, you can see that it's essentially flat. So resistivity derivative with gate voltage should be 0. And that's what we see. If we measure at high temperature, around 60 Kelvin, the thermal power is actually going to 0 at this point and at this point. Okay. So now I start cooling the system to less than 60 degrees and 35 Kelvin. You can see there's a small additional component which cannot be explained by the semi-classical model starts to emerge. You can decrease it 20 Kelvin. You can clearly see now there is an additional peak over here, an additional dip here that says that your thermopower cannot be explained by a simple derivative of the resistance with respect to density. This goes further, and you can see at 10 Kelvin, there's a very strong dip, and there's a very strong peak at minus and plus dense NS, which is clearly shows that the Boltzmann semi-classical model is failing, and we are no longer having a simple diffusive metal in our system. Okay, so I'm going to compare this with the calculations from the semi-classical model. You can see the pink one is the calculation, and the gray color is the data. You can clearly see that it more or less agrees at most of the points in the Moire band, except when the filling factor is near half filling. And this is what you call an excess thermopower. Now, excess thermopower essentially means that there is, in some sense, that there is an additional entropy of the system. And this entropy is not going to zero when you reduce the temperature, which is one of the puzzles that even systems in high TC superconductors have seen. So you can see as a function of temperature, the thermopower is tending to a finite value rather than going to zero, which happens, by the way, at other filling factors. Say when the filling factor is 4 or 3, you can see they essentially extrapolate to zero, when the temperature goes to zero. Okay, so this is a non-vanishing thermopower, or it means a non-vanishing entropy as you go to lower and lower temperature. And hence, the question that arises that whether at half filling, you have a quasi-particle that are well-defined or not. So this question has been asked and various other aspects, and I'm not going to go into that detail. What we see is, I just want to say that there is a limit called a Planckian limit in the half filling, in the strong correlation limit, where the electron-electron interaction poses a serious question about how well-defined your quasi-particles is, and the dissipation reaches the maximum because your quasi-particles are no longer very well-defined. So we find that this probably is a system which has got a very strong similarity to those kind of what you call a strange metal. And we essentially found that that region is near the half filling where the electron-electron interaction is very strong. Okay, I would like to come to quickly for this part. I just wanted to say that this has been taken forward significantly by my colleague Chandni and other students, and recently there were new phases were discovered at half filling. So you see, I showed you half filling means NS of 2, but there are new phases in the systems have been discovered which are obtained at 3/4, 3.5 filling. So there is a huge amount of work that's going on in this direction. I would like to show you there are two aspects. One is this, that if you create a strong spin orbit interaction in this twisted bilayer graphene, you get new hierarchy of states at 3.5 and plus minus 3.5, which are not understood where those states coming from. In addition to that, there are new topological phenomena that is coming up where you can create minimally twisted bilayer graphene and create topological channels in graphene through reconstruction of the lattice structure. And that leads to this beautiful one-dimensional channels, and that gives you Aharonov-Bohm, because they are network, it gives a nice Aharonov-Bohm effect that we have been looking at. So I want to look into, I just want to get rid of this part. So I want to come to the technology roadmap, because I promised that this is something which is very close to my work these days. So, and because this meeting is done in collaboration with the Carbon Society. So where is the technology going? It's very interesting physics. There's no doubt about it. And I showed you the new phases that you can generate in graphene. But where is the technology coming from? And if you look at the European Graphene Flagship Program's 2020 report, you'll see there are many directions in which graphene and 2D materials are becoming important. For example, you have got composites, and starting from functional coating to structural material, construction material, water treatment and desalination. We have got energies, we have got batteries coming up, photovoltaic, flexible cells, perovskite photovoltaics. So there's a huge region where graphene can be, and 2D materials in general, graphene in particular, can be used. Of course, data communication, electronics, you have got high frequency electronics already, flexible devices. There are possibilities of low cost printable electronics. And you can see the rough time scale that people are looking at these days. It's about 2030 and beyond. Imaging and sensors, for example, you can clearly see the fast charging batteries, then the CMOS-based cameras, and probably at some point of time, somewhere around late this decade, one is looking at autonomous cars. Okay, and the biomedical, of course, the diagnostics and biomedical applications are neuromorphic, in particular, is becoming a very, very strong areas of development of R&D. So you can see there's a huge amount of possibilities that exists. And as a result, there are now nearly 350 2D related companies all over the world, and it's increasing. We have some ways of creating this in large scale, which is either epitaxial growth or chemical vapor deposition, and now even other kind of two-dimensional materials like molybdenum disulfide and tungsten disulfide and so on and so forth that are being created at wafer scale, and that's leading to a strong emphasis on whether this could be integrated to the silicon processing. Okay, so this is something which we will follow. But I think before that comes into market, there are larger possibilities of bulk scale applications of nanomaterials. And there are key problems in this. If you look at the cost of these two-dimensional materials, it's actually horrendously large. For example, you have graphene, which is Europe, China. China is much lower in some cases. India is about 0.4 grams per dollars per gram. You have US, Europe selling at $20 per gram to $200 per gram. Boron nitride is even higher. So there is a huge amount of cost that is involved in making these materials. And as a result, one has to overcome that challenge. Whether you want to do high quality physics or high quality technology, one has to start looking at the cost benefit ratio. So what are we looking for? Production, for example, today, our global capacity of making graphene is about 2.5 kiloton per year. The demand, because there is a very niche market, just about 300 to 400 ton per year, and probably in about next 5-6 years, it's going to go to about 10 kiloton per year. But is it enough for applications? Well, I mean, this is mostly coming out to be, one has to wait and see. What is extremely important when the graphene market develops, and this was mentioned when we started this inaugural remarks, quality and standard. Right now, there is no quality and standard universally accepted protocol. And this is one of the major problems in graphene manufacturing industry. Okay, so we have to enforce a standard. There are companies which are saying that they are producing graphene, but they are essentially graphene plates, or they are essentially graphene nanoparticles. Okay? So one has to come up with an universally accepted enforcement or enforcing standard, and that has to happen within the next few years in 2026 to 2030-ish, if graphene has to come up as an universally accepted material system. Cost and pricing, of course, this is something which is open. The graphene nano plates, which cost about $30 a kilo now. And if you want to make a realistic application, it has to come down to less than $10 a kilo. Okay, I'm quite amused by the fact that I started with a twisted bilayer graphene, and I'm ending this talk with how much a graphene should cost. But it's anyway, I mean, this is a realistic approach, so one has to do that. And finally, applications. What kind of applications of graphene that we are going to see in the next few years? For example, I think the first one will come in car tires, because once our capacity will improve to about 10 kiloton per year, we would see probably first car tire to roll out. We have a comparison, because now we are using carbon black. I think Dr. Bahl is there. He would know all these very, very accurately about where the carbon black is being used and what kind of cost that we are talking about. But the comparison between carbon black is imminent if you want to use this in car tires, automotive parts, and so on, these kind of applications. So printable electronics is probably next, textile, concrete, probably other applications, and polymer, elastomers, coatings, insulators, anode materials in terahertz battery, and all these technologies can get completely revolutionized once we reach a global manufacturing capacity of about 100,000 to 1 million ton a year. This is where we need to create an ecosystem and a proper network where how one can go for very large manufacturing. And I think Reliance has been sponsoring this, which is excellent to hear, because much of my work started with Reliance, a collaborative project from the Reliance Industries about 5 years ago. And that's when we started this work, and how do we create a new way of massive production of graphene. I'm happy to say that now we have a company on this, because we have found a new way of creating high quality graphene from pure water as a source, as a medium, and which is more than 2 or 3 times more efficient in producing high quality, pristine quality graphene and other 2-dimensional materials. It has led to a company now, and I would like to see that if this can lead to more impact on the graphene and 2-dimensional technology. Okay, I'm going to stop here. Thank you very much for your attention.
Well, thank you so much, Professor Ghosh. You have really enlightened everybody. I'm sure the young minds who are engaged in the R&D and production of this material must be feeling excited about what this material is capable of offering in the years to come. You have really elaborated on fundamentals as well as the applications and what we are doing, what internationally is expected in terms of production. Thank you so much for your wonderful lecture. And we really appreciate your having joined us and spared time and shared all your latest results with us. Thank you so much, Mr. Ghosh, once again. Thank you. I don't know if people are ready with any questions at the moment. Audience is welcome to ask 1 or 2 questions. I'm sure Professor Ghosh will oblige the audience.
Thanks, Arindam, for the nice talk. I have one question regarding,
can you identify yourself, please?
I'm Gopal, so he understands. Sorry. Yeah. Right. I just want to ask, so do you see any applications, or how far away are we from getting good quality so that we can have some resistance standards or something like that? So we do not talk about those things yet.
Resistance standard has already been done using graphene. The NPL UK, for example, they are deeply involved in making high quality resistance standard with graphene, and they have achieved about 3 parts per billion as far as I remember.
But still not accepted. Still not accepted universally like a QHR, for example.
Correct. So now the graphene mobilities are so high. I mean, Mandar is a global expert in this, and he might tell you better on that. I don't think it's the graphene is an universally accepted material standard. It's still the high mobility semiconductors. But as far as the electrical mobility of graphene is concerned, that is already at the level or close to that level. About a few million is the mobility, which is getting to the ballpark of the high quality semiconductor heterostructures.
Yes.
Yeah, Mandar has
sent a reference. Thanks, Mandar.
Well, thank you so much, Professor Ghosh, once again. We all appreciate very much and thank you profusely for this. Thank you. We now come to the next invited lecture, which is being given by Professor Deshmukh. Professor Mandar Deshmukh is professor at the Tata Institute of Fundamental Research in the Department of Condensed Matter Physics and Material Science. Professor Deshmukh has been an experimentalist working in the broad area of condensed matter physics and material science. And he has been a faculty member at Tata Institute of Fundamental Research since January 2006, and has he graduated research. His graduate research for the PhD was in the group of Dan Ralph at Cornell. And then he has been a recipient of several awards and honors, the latest being the Oxford Instruments Young Nano Scientist India 2019 award. Congratulations to you, Professor Deshmukh, for this. Then he's a fellow of the Indian Academy of Sciences and also Shanti Swarup Bhatnagar Awardee 2015 in physics. I now request Professor Deshmukh to address the audience with his lecture, which is Quantum Noise Limited Amplifier using Graphene-Josephson on junctions. We thank all yours for half an hour, Professor Deshmukh.
Okay, thank you, Dr. Bahal, and all the organizers for having me here at this meeting to talk about our work. Let me get started. Let's see. Yeah. Okay. Hope you can see my screen. Okay. Okay. So I'm going to talk about some very recent work that we have done with graphene in a direction quite different from what Arindam talked about. So I thought it might be interesting for the audience. So what I'm going to tell you about is how graphene-based Josephson junctions, and I'll explain what Josephson junctions are as we go along. Essentially, you proximatize graphene by connecting it to superconducting electrodes. You can actually make amplifiers using these, and these amplifiers are very critical for studying qubits, as I will explain a little bit later. This work has recently appeared online on Nature Nanotechnology, and it will be in the November issue of Nature Nanotechnology. So I gratefully acknowledge support from Department of Atomic Energy and Department of Science and Technology of India, which really makes our research possible. So at the outset, let me acknowledge the actual people who do the work. As I always say, professor like me don't do any work. I'm grateful to have excellent collaborators and students. So Joydeep is the student who led the work. This person right here. This is a photo from our trek about 2 weeks back. And he led the work on these, and other people from my group, Supriyo, Shubhamay, Alicia, and Ipsita contributed. And my collaborator for this work is Vijay at TFR and his student Kishore. And for making these devices, we use the hexagonal boron nitride, excellent hexagonal boron nitride from Dr. Watanabe and Taniguchi. So this really makes the work possible. So let me briefly tell you a little bit, a few sentences about what we do. We work on different aspects of nanoscale electronics, starting from low frequency DC electronics to RF electronics. So we study twistronics in similar flavor to what Arindam mentioned, and quantum transport. We look at nanomechanics, which is the mechanics of membranes which are only 1 atom thick. We look at magnetic excitations, just like electronic excitations. The magnetic excitations, spin waves, are interesting physics and possible technology platforms. And superconductors are something that we have been focusing on in the last 6 to 7 years. So high temperature superconductors down to the single unit cell limit is something that we find really exciting. and the graphene-Josephson junctions, which are essentially graphene connected to superconductors to make kind of proximatized Josephson junction. And today I won't talk about any of the other stuff. I will focus on this particular subtopic of research in our lab, which is graphene-Josephson junctions and how we made an amplifier using this. So let me give you a brief background. So when one wants to measure signals from quantum states, one wants to identify whether the system is in, say, the ground state or excited state. And often the electrical signals that come out of these devices in variety of different qubit platforms is actually very small amount of power. Electrical signal is actually coming out, and it has to be amplified. So this is about 0.1 femtowatts. So it's very small signal, and it needs to be amplified all the way from low temperatures of 10 millikelvin to electrical signal of about few milliwatt at room temperature. So there's a chain of amplification. But we know from basic electronics, nothing particular to either qubits or anything, that anytime we amplify an electrical signal, this is basic electronics, anytime we amplify a signal, you automatically add noise, which is, kind of has a characteristic of that particular amplification technology. So now this noise, you cannot eliminate this noise. That's a fundamental, even quantum mechanics will permits some minimal amount of noise. So you can basically go down to that level. So if you use a chain of amplifiers, one amplifier, another amplifier, you don't beat the problem, but you can minimize the noise. So each amplifier has a noise which is characterized in terms of its noise temperature. So if I look at the noise coming at the final stage, it's a kind of a function of the gains in the chain. This is gain 1, gain 2, however many amplifiers, and the noise temperature, which is basically the noise added by the amplifier, is quantified in units of temperature. So bottom line is that the noise from the first amplifier makes a difference, because you can't get rid of this, okay? And all other contributions become small. So you want this noise to be as small as possible. And that's actually where the parametric amplifier that I talk about will play a critical role. So this development of this parametric amplifier using aluminum oxide based tunnel junctions has led to several interesting experiments. So the parametric amplifier is not new, okay? So it's been around for quite some time, but our implementation is interesting, and it has some additional flavor, which is what I'll tell you by the end of this talk. So the parametric amplifier has enabled lots of experiments which or studies of qubits, particularly superconducting qubits and charged qubits like this work, which would not be possible without this minimal noise amplification scheme. So what is a parametric amplifier is that, as you will see, a circuit implementation. So we know that a mass attached to a spring can have a differential equation which sort of, kind of described like this, where x is the coordinate of the motion of the spring. But what is important is these nonlinear terms, which often we ignore in the first course in classical mechanics, but these lead to very interesting physics, and there are analogs of this physics that I'm going to talk about in a lot of different aspects of physics, including optics. The bottom line is that because of the presence of this term, you can have a spring which is tunable, and it can actually be tuned parametrically, and that's why this term parametric amplifier comes about. Okay, so when you have a parametric amplifier sort of equation, this is a nonlinear medium. So if you put in some two electrical signals or optical signals, you actually get some nonlinear processes where you'll get a signal, pump, an amplification, and some other electrical signal called the idler signal. So the platform that we use is a kind of a Josephson junction, which is coupled to a capacitor, and you kind of make an oscillator out of it. Effectively, the differential equations are the same as what I just described to you. And this oscillator is a nonlinear oscillator, and at the boundary of cusp of becoming kind of multifunction, you can realize amplification. And that's sort of the heart of it. And it's been realized using superconducting tunnel junctions for lots of interesting physics. So the tuning knob has been used as magnetic field, which is problematic in some cases. So, and our experiment kind of gets around it. So again, go back to the driven harmonic oscillator. The advantage of a parametric system is that it can lead to amplification of the electrical signal. And one way to think about is that this term is kind of a reduction in damping, which is another way of saying there's amplification. And there are simple analogs of it. You know, how you increase the amplitude when you are in a swing is basically an example of this parametric driving of a mechanical oscillator. And this parametric driving can, essentially modulating the stiffness of the system can lead to amplification, just like you increase the amplitude of motion in a swing without any external pushing, you can get amplification. Okay, so what we have done is use a graphene-Josephson junction, which is graphene connected to superconductor, and because the physics, which is the physics of Andreev bound states, you basically, even though graphene itself is not superconducting, it can sustain a supercurrent through it. And the supercurrent has a relationship with the phase difference of across the two superconductors. And this is the governing sort of property of the system. Now, the peculiar property of this current phase relationship is that it's unharmonic. If it was just harmonic, we know that if we make an oscillator by parallel capacitor, you'll get equidistant energy levels. But if it's not unharmonic, you get unequal spacing, and that is at the heart of all of superconducting electronics, because all they do is for the 2 qubits, you use only the lowest 2 states. And for amplifiers as well, we use the same idea. So there has been a lot of interest in the last, I would say, 4 or 5 years trying to make Josephson junctions using graphene and its properties. People have made simple Josephson junctions, even demonstrated a qubit using transmon qubit using graphene Josephson junctions, because it has some advantages, but turns out it's extremely lossy for a qubit, but it's good for amplification. And it has been used as a bolometer. And so it has a lot of interesting properties, and that's why we got into it. So the way we make these devices is somewhat similar. This is for a twisted device, but we don't need a twisted device for this, but I'm just going to give you a slide. We assemble this like a Lego pieces. We take boron nitride, sort of like what Arindam explained. We pick up one layer of graphene, and if I were making twisted devices, I would pick up another layer, and we sandwich it in boron nitride to get the device. And it looks like this. I've shown you some representatives. There is some 2 layers of boron nitride, trapped in between is graphene, and now one can make devices out of it by etching the boron nitride and making electrical connection. So because we are going to make an amplifier which works at RF electronics, we have to design waveguides for the RF electronics to kind of carry electrical signal. So this is our Josephson junction. This is the capacitor. This is a gate electrode, which tunes the properties of the Josephson junction, and it looks like this. So this is the stack that I showed you. There are 2 superconducting electrodes, source and drain, separated by molybdenum rhenium, sort of graphene bridged by molybdenum rhenium, and the separation is about 200 nanometers. So that allows us to kind of make the Josephson junction. So in the cross section, it looks something like this. Now we can now start to do the measurements. The effective circuit looks something like this, which is a inductor in parallel with a capacitor. So to do these measurements, we cool the device down to millikelvin temperatures using a dilution fridge. And I won't go into all the details, but one has to carefully kind of design the RF measurement circuit to enable this, which is anyway, if you were using a qubit and using this amplifier, you would anyway do it in a dilution fridge. Okay. Now, when we start to do these measurements, the first measurement that we can do is measure the DC, which is low frequency electrical measurement of the graphene's electrical property when you contact it with a superconductor. And what you see is this is the current driven through the Josephson junction. This is the gate voltage. And you see a region which is of superconducting region of the junction. And here you switch the junction into the normal state. And in this particular device, the set of devices that we make, we have optimized the process to have extreme transparency on the electron side, but that actually on the hole side, we get a Schottky barrier. So there, we don't see superconducting branch, but this enables a very nice amplifier working in. So once we hook it up in parallel with a capacitor, you have an essentially a resonator, a peculiar kind of resonator, and the resonant frequency of that resonator is now tunable with gate voltage. The reason we can tune with the gate voltage is because as I tune the Josephson junction's property with a gate, its inductance changes, and that inductance, so you can think of this Josephson junction as a tunable nonlinear inductor. So the resonant frequency can be tuned all the way from 2 gigahertz to about 5.5, 6 gigahertz, and to position it to amplify the signal exactly where you wanted the amplification to happen. So now we are ready to do the measurements with this amplifier. So to make it work like an amplifier, we have to actually pump it to drive it into extreme nonlinear response. And that's sort of what is shown here. It's a little bit technical, but I'll try to explain. So there's an oscillator, graphene Josephson junction, which you want to drive very nonlinearly, because that's precisely the point where it starts to behave like an amplifier. So this shows a phase response of the parametric amplifier as a function of frequency. And at this point, it is sort of primed to give very large gains, work as an amplifier. And so this is the response of the device, where you can see the gain. The gain is about something close to 23 dB gain. And it has a bandwidth of about 10 megahertz or so. Okay. So there are implementations of parametric amplifier which can be very broadband, and by modifying the starting parametric amplifier. But this kind of amplification is common for parametric amplifiers. What is more interesting is something which I use to motivate the talk is the noise temperature, which is in this red dots and indicated on the y-axis. So the noise temperature of this amplifier is about 0.2 Kelvin, okay, or 200 millikelvin. This is basically very close. The green dashed line is the quantum limit. So our amplifier is actually working at the quantum limit, adding the least allowed noise permitted by quantum mechanics. So you cannot normally, you cannot basically beat this quantum limit of addition of noise. So this amplifier is a kind of state of the art, and it provides large gain, is quantum noise limited, and is tunable with a gate voltage. Unlike applying an application of magnetic field for Josephson junctions, its saturation power, which is basically a metric which benchmarks amplifiers, is actually pretty good. It's about minus 120 dBm. So we can demonstrate that this amplifier works over a large part of the range where the amplification is 20 dB or more, and it's tunable. It's an amplifier whose band of operation is tunable over several gigahertz, and this can be improved even further going forward. Now, you might say, where is this interesting? So these kind of parametric amplifiers are very useful in environments which with a large applied magnetic field, where graphene-based parametric amplifiers are more robust and can be used. They can also be used in applications where one wants tuning without any amount of stray magnetic field, because the parametric amplifiers, other squid-based parametric amplifiers, will have some small magnetic field. So this amplifier is state of the art, comparable to the best that's out there. So I will skip this slide. It talks more about the physics of these Josephson junctions and how it arises, but I can talk about this if somebody has a question, but I'll skip this now just because I want to finish in time. So let me briefly summarize what I told you about. Some of it was technical. I kind of skipped the details just to make it accessible. But the main message of my talk is that we have an amplifier by proximatizing graphene and making shunting it with a capacitor and making an oscillator. It provides gain of higher than 20 dB. It's quantum noise limited. And more than what we have just demonstrated, there are possibilities to make some exquisite sensors, quantum sensors, embedded inside the amplifier. And that's something that is our focus, already, that we are interested in working towards over the next couple of years. So that's basically all I wanted to talk about. I'll stop here and take any questions. Thank you very much for your kind attention.
Yeah. Can you hear me now?
Yeah.
Yeah. Thank you so much, Professor Deshmukh, for a very thought-provoking lecture. And also, I see a lot of applications of this material. I don't know, I would like to, it's not a question, it's just an inquiry. Has this been being applied actually in commercial side?
No, we are actually in the process of starting a company to make these kind of devices.
Very good.
Using graphene. It's not a reality yet, but hopefully soon. We have to wait for some permissions to, at the FIR to start a company as a faculty member. We have to get permission, so I'm waiting for that.
That's very good. Very good. We look forward to that, actually. That's one of the things we wish to see it happening. Mm-hmm. Any other question? Maybe Professor Venugopal wants to ask something.
A very quick clarification. What temperature are these operations?
So these are the Josephson junctions can work up to few Kelvin, but this paramp sits at 10 millikelvin or 20 millikelvin, and these typical HEMT-based amplifiers will have a noise temperature of about 4 Kelvin. These have a factor of roughly 20 smaller noise temperature.
Thank you.
Any other question from the audience?
If anybody has any question, I welcome any question. No question is bad question as far as I'm concerned.
Maybe I can ask a quick question to Mandar. Is it okay, Dr. Brown? Can you hear me?
Is Arindam?
Yeah, go Arindam.
Okay, good. Mandar, thanks. You told me about the work, but it was nice to look at the details. Very interesting. So, quick question is the sensors. I'm guessing you are talking about the temperature sensors. Is that correct? So
there can be power sensors. There can be actually any excitation. Either it can be magnetic excitation, because this amplifier is inherently non-linear. It is susceptible to perturbation, and that's the sensing mechanism. So the non-linearity makes it sensitive to. So the immediate thing that we are working on is a kind of bolometer that beats existing bolometers with higher noise equivalent power. But we have several other ideas that I don't want to go into too much detail in a public forum.
Okay. Okay. Yeah. Maybe you can communicate one-to-one later on.
Yeah, sure. I mean,
Yeah.
anytime. Yeah.
Yeah. Yeah. Well, if there are no other questions from the audience, let us thank Professor Deshmukh. You have been very kind and sharing with us all the latest research that you have done, and that has a very commercial side to it, which is very interesting. Thank you so much once again, and very kind of you to have shared your knowledge with us. Thank you. Thank you. We now move to the oral presentation session, which is basically energy storage is the main topic of the session. And the first lecture is being given by Dr. Tanarapu Venkata Anusha from ARC International, Hyderabad. And the topic of the lecture is N-doped carbon nanomaterials as anodes for advanced sodium-ion batteries. Very interesting. Do we have the, hello?
Hello, sir. Is my voice audible?
Yeah, we can't see you, but we are able to hear you.
Shall I switch to?
Start your video, Doctor. Anusha, switch on your video first.
Yeah.
Yes, sir.
Your video is still on. Open your video.
Sent you the request to starting your video. Please start.
Otherwise, go ahead. No problem.
Ashokji?
No.
Sir. Sir. Hello, sir.
Yeah, it's coming.
Good morning, sir. Good morning, everyone. Coming to my presentation, N-doped carbon nanomaterials as anodes for advanced sodium-ion batteries. Commercialization of the sodium-ion batteries is the critical challenge due to the lack of appropriate anode that allows the fast sodium-ion diffusion. As of today, various kinds of carbon-use materials have been widely studied. For a long time, use them as a ultra-active material. Ultra-active material for electrochemical energy storage applications like fuel cells, supercaps, lithium-ion batteries, and sodium-ion batteries. Because of distinctive electro and physical properties of carbon-use materials. Carbon-use materials have properties like easily available and abundance in the earth crust and fair electrical conductivity. Respected sirs may also know about the introduction of carbon materials and batteries. For the sake of some of my friends, I am giving this introduction of about the carbon and batteries. The word carbon is derived from the Latin word carbo, which means charcoal. The element carbon is widely distributed in the nature. It is found in the earth crust in the ratio of 180 ppm. The element